So in this video or the series of videos, I've titled it as this slightly provocative, the quest for 1000x speedup. So two caveats. One, this quest is not complete. I don't have the solution. I don't have a 1000x speedup, but that's what I aim to do, though I'm not there. Now, what are we talking about, right? If you don't have any context, this is a follow-up where we are looking at a MATML and ReLU example on CPU. So this is a follow-up to my previous series of videos on MLAR running tutorial. So the videos are linked here. Specifically, I ended part 4 with this kind of a clickbait ending, and I'm continuing that in this video. Okay, so all of this is again a follow-up to the original Alexander Singer's beginner tutorial, where he talks about how you lower and run basically various optimizations that you can do for a simple linear algebra use case, a simple MATML followed by a ReLU example. And in this YouTube series, in my older tutorial, I basically showed how you run the program on a CPU, right? Like basically going from LIR to CPU code, and in this one, we are specifically looking at improving performance of this code. So, like the caveats to repeat it again, we're only going to look at CPU. We're not worried about GPUs. And we have the simple MATML plus ReLU example and with the simple input size. So we're just going to work with this example. Now, where are we in our journey, right? So the point is, last time I ended the video saying that while lowering and optimizing gave us basically optimizing because using affine fusion and tiling gave us a little bit of performance improvement. But the problem was a naive, simple three nested loop implementation in C++ using just naive G++ was already pretty good, right? So the performance, they're all in the same ballpark. So the MLAR version was not faster, right? So my question was, how much faster can you be, right? How good are these numbers? Can you do better? What's the baseline, right? So we stated, how much can I really achieve on the hardware that I have? What's the good performance? And how close are these numbers to that good performance? So how do we do that, right? So let's start with the obvious optimization. So the first thing I did was basically bring in Clang instead of LLC because I discovered with some play testing that the LLC's defaults were not good. With Clang, I could bring in optimization flags and so on. So I could bring down these numbers down to this ballpark, 400 millisecond, right? So that's pretty good. There's a lot on the table. But how much more can we get out of this hardware, right? That was my question. We are at 400 milliseconds, the best we have with this MLIR version lowered simply to CPU. So I thought that good baselines, because we're doing it with MATML and ReLU, would be NumPy and PyTorch, right? So these are obviously industry standard software. And the numbers I got with NumPy, it was basically 2.5 to 6 milliseconds. So if you go back, this is at 400 millisecond, and with NumPy we have reached a performance of 6 millisecond worst case. So that's a huge jump, right? And what about PyTorch? So PyTorch has, if you know, there is a concept of torch compile. So we'll talk about more of that in later videos. But PyTorch Eager, the default version, took around 0.7 to 1.3 milliseconds. It's crazy. And in compile, that number went down further and max of 1 millisecond. So these are the numbers I observed. Now obviously my immediate thought is these are some complicated piece of software, right? These are some very mature piece of software. Obviously, there are a lot of optimizations. So let's look at some more baselines, right? So hopefully more smaller code bases and not top of the line industry softwares. So, so I picked up two or three more baselines. So basically, NumPy, if you know, is based on these BLAST libraries usually in Fortran, like OpenBLAST. I wanted to try those, but that was very difficult to approach. So instead, I picked other similar BLAST libraries. So two of them, Eigen and Flame Bliss. So both of these are in C++ and lower, so not Fortran, easier to run. And because we had PyTorch as a deep learning library, I picked the other simpler deep learning library, which is GGML. So if you've heard of llama.cpp or olama, this is the library that powers it. So this is purely meant for pure CPU kind of workload. So I thought that that might be more fair this line to also include, right? So let's show you the numbers for all of these softwares. So starting with Eigen. So Eigen achieved 6 milliseconds, which is great, which is same as NumPy's performance. Now the other pieces, the Flame Bliss and GGML, I could control the threads, right? I could basically control the number of threads when compiling. And so I was able to, run on a single thread versus multiple threads because we don't know if the performance improvements coming from there. So Flame Bliss single thread was 3 to 6 milliseconds, and basically using 4 threads with either OpenMP or pthreads, the performance like improved to 1 millisecond. In comparison, the GGML library was in single thread 3 to 9 milliseconds, and 4 threads the number goes down to 2 to 6 milliseconds. So there's already a pattern, few patterns you can see here. Firstly, adding more threads does reduce, I mean, does improve your performance, but it's 2 to 4 times, right? Understandable, 3x believable numbers. So single thread 6 millisecond, we can kind of already conclude that NumPy is in the same ballpark. So NumPy also is single threaded, right? And so then the question is, where is all this performance coming from, right? If it's not, if even single thread can get 6 millisecond, but our version from coming from MLIR, with my assumption being we already doing fine loop transformations and optimizations there, tiling, cache aware tiling, and so on, and yet we have this huge discrepancy. So where is this number coming from? Where is all this performance coming from, right? And so basically, as I said earlier, it's not from multi-core, it's instead from vectorization. So basically, we will go a little bit, I'll show you a little bit example of vectorization, what that means. But the idea is that even CPUs have a few different SIMD intrinsics. So that means vector processing. So instead of scalar processing, where you're adding two elements, you're adding two vectors in one go, right? And these are basically CPU intrinsic capabilities. So basically, this is hardware. So a vector of instruction of basically vector 4 means you can add 4 elements in one go without taking more time, right? That's extra hardware in your CPU that we are not using right now, apparently. So I'll take a quick pause here and give you an example of AVX2. There are a number of different intrinsics. So I'll do that now before we proceed with the rest of this video. So let's see this example. But before I do that, I'm going to show you the list of x86 SMD instructions so that you're on the same page. So basically, in different years, Intel and AMD, and they've introduced these different kind of extensions, right? So each of these is like a family of related instructions that you can use. So SSE, SSE2, SSE3, and if you go down, you have the more newer ones, AVX, AVX2, AVX512. So the idea is each of these is basically better technology and it's giving you wider registers. So for example, in AVX2 you have 256-bit vector variants, while in AVX512 you have 512-bit wide, which means if you're going to add say 32-bit integers, you can only do 256 by 32 here, 8, and but you could do 16 here in one go. You can basically add 16 elements in one shot. And of course, recently we have newer matrix extension, basically matrix multiplication, because deep learning has become so important, right? Now, so on my machine, so just to show you, of course, this is my, I'm in WSL, but still, when you run LSCPU, so you get information about your CPU architecture and all of this. But if you see here, you also have this bunch of flags. And in this list of flags are some of the SIMD instructions availability. So for example, if you see here, this shows that this machine has AVX2 in the hardware, right? And we also have AVX2 512, AVX2 512F, which is floating point extension, more things, right? I also don't know what all of these things mean, but you have a lot of these intrinsics available on this machine. This is important because the example I'm going to show you. So basically, I'm going to show you an example of adding using AVX2. So this is there in this repo. So when I created this example, I was doing that on a machine which where AVX2 was the best, right? So that's why I wrote the code. If you see here, this machine that I'm using recording this video on actually has is more, it's a newer machine, so you have even more newer intrinsics, but that's okay. Now, how does it work, right? So what do you change in your code? So if I go here, so in this repo, in this main.c, I'm going to see this example. And so basically I start out doing things normally. So if you see here, we are creating random numbers into arrays A and B. And these are very big arrays, so large number of elements. And then we basically add them normally. Right? This is what you do normally. We're just looping from 0 to n, and c of I is equal to a of I plus b of I. So this part of the code is basically how you do it normally, right? Now, when you want to use vector instruction, so basically you have to import this header, intrinsics, and you have to then manually write code which would use whatever element instruction that you want, right? So you see here, what I've done is I'm going to use the avx2 instruction set, which means, so basically I have 256 bits that are available, right? So what we do here is we are going to loop, but this time jump over 8 elements. So every time we're going to load from that a array, a of I, we are going to use this instruction mm256 load si256, which means it's going to load a signed integer uh, into this into that register of 256 bits, which means it's going to load 8 because this integer is going to 32 bits, right? So then what's happening here is you basically load all of this into this vector. So you have to load a and b, obviously, and then finally you have your actual compute, which is the addition, right? And we are saying addition by using this particular instruction. So this add underscore API 32. So basically you need to specify what you're adding here. These are two 32-bit integers that you're adding. And once you're done, the result, 8 of them would be present in this C variable. And we have to bring that back, store using the store instruction back into our normal C array. And this becomes the equivalent code using vector instruction, right? So if you see, there's one more thing to call out. When I created the original pointers ABC, I had to do one extra bit of work, which is to ensure that they are allocated aligned to the 256-bit size. Otherwise, the register would not be able to load 8 of them in one code, right? So it's just a bit of thing you need to do before you can start. Now let's see what this means on my machine. So you see here, basically, I can show you the README. Go back. Yeah, the instructions here to compile it. So you can't just run gcc main.c. You have to add the fact that this architecture, this you're going to take advantage of this instruction set. So that gives you that, and then I can run it. And so basically, we have big sized vector. Actually, I'm calling it matrix, but that's not right. But you see here that the basic addition, the manual for loop takes 3500 microsecond, but the avx2 version only takes 500 microsecond. So it's kind of like loosely 7 times faster, right? Because you're just adding 8 elements in one go in one shot. So this hardware was always there in my machine, but unless I write code to exploit it, I'm not going to be able to get this benefit. So that is this example. Now, of course, you saw that here we used particular code to get this. So you might wonder, how do I get that code? So there's this nice reference. So basically, I've linked it in this repo as well, the guide to intrinsics. So here, you basically have the different instruction set color coded, and you can search different categories. So basically, you can search for the thing that you want. So what we were doing was AVX2, so this one, and so let's say the thing we're doing was add, right? So basically, you get all of these instructions that are available. So I use this one, which is 32-bit integers. But if you see here, you also have 16-bit integers. So let me open this one. So basically, it's giving you a quick look at what this is. So you have the hash include, and you have this function that we did, and it's saying the CPID flag, and this is the actual instruction that is emitted. And we can actually verify this, confirm this basically by going back to our code and doing an object dump. So I'm going to object dump disassemble a.out, and this is going to be listen. So basically, we have bunch of instructions here through the code. There's a lot of stuff here because we also had um, the normal version, the naive version, but I can just search for this, right? And you see here, this is this is the exact portion which refers to the vector function, right? So basically, the move part move 8 integers into the register, and then to do the addition, and then to move back. So you see here also this reference to the register names, which are YMM series, and it's called out here also, I believe in this Wikipedia page, for example, that the different variants actually use different names for the register, so that it becomes kind of like obvious. So maybe in this case, you look at this and you kind of know which one you're dealing with. Um, so there is, for instance, if I open this version, so this would be basically a 16-bit integer addition. So what we're doing is basically doing the same vector add, but this time not with 8 32-bit integers, but 16-bit integers, right? So this kind of shows you the pseudocode of what is happening in that. So I'll just show here one more thing which I added to this code to LDBug. Um, so basically, one way for you to confirm this, because reading object dump might be confusing, especially if you don't know what instruction you're looking for. Basically, I realized that you can literally like add go to target uh, directly with raw ASM. So with this command, you're basically just emitting raw ASM instruction like a go to label, which will not use uh, before and after the section that you want to examine. And if you do this in the hex dump, if I go back, you will see you see these labels. So there will now be a label. So if I make after. So there is a label now after plain, which is added literally after that name for loop. So this is before plain and after plain. So this basically tells you that this part of the assembly code directly corresponds to that name for loop. And you see you have simple adds, moves, and the basic stuff. And I can just go to the next iteration, which is plain before AVX. So basically this portion before AVX to AVX is corresponds to that code, right? And you see here in this portion, we have the V versions, the vector versions of the instruction. There is one more thing I'll just mention while you're on the topic, because this confused me when I was searching for the instruction, not for this AVX2 case, but in some of the other cases of vectorization, because I wanted to know if I could understand this instruction just by looking at it. So what I understood was V is vectorization, obviously. P is fact, add ADD is fine, but then D stands for double, right? Which was confusing me because this is 32 bits, right? Not 64 bits. And then I realized looking at the other instructions. So if you see here, this, if you see 16, so 16 is add W word, and 64 is Q, which is like something else. And then I kind of put two and two together. Basically, what I realized was AVX2 is very old. So at that point, Word was 16 bits and W word is 32 bits, and not what we have today, where Word is 32 bits and W word is 64 bits. At least that was my interpretation. I don't know if this is correct, but the logic seems to kind of work out. If you go to one of the newer ones, so I'll go to the AVX2 family and pick, let's say, the AVX2 floating point ones, and let's search for, okay, I don't think that's right. Is this the one? Okay, this is the one. So here, if you see, there is, I think, it seems to me that the convention is still the same here. Word is 16. Where is my 32? You see the Z registers here, but this is still double. Okay, maybe then the convention is always the case. Maybe it's always the case that 64 gets marked as Q. Okay, that kind of makes sense. So basically, that seems to be the convention. So you can use that to figure out what size of the bits, or of course, you can just look up the documentation for the instructions. Okay, so I think that is quite a bit of digression, but that is an intro into vectorization for a simple case of addition. Now, the challenge is what we want to do is basically we want uh, to get vector instruction out of our MLIR pipeline, because right now MLIR is getting lowered to the normal CPU instruction. So there is a long story. I am going to have subsequent videos talking about this. Specifically, there is a dialect in MLIR called vector, which is supposed to help with this. But there is also a concept of auto vectorization, which is basically how do you automatically vectorize. But my experience was that these things were not working the way I wanted to work. I couldn't easily get to the point of emitting vector instruction starting from RMLIR code, especially when you have these other optimizations like fusion and tiling also, right? So, so the point is uh, there is a trade-off in general. We didn't go into details here, but all of the other libraries I showed, like Eigen and NumPy and VDML, so they all kind of rely on handwritten platform-specific solutions, which means they're very fast. That's how you get out of the box. NumPy or Eigen is able to get 6 milliseconds, right? But they're not generalized. You have to write code for each platform, for each. You need to have if conditions, and you have to see if your CPU supports it, and then you have to there's a lot of work, right? So the other end of the spectrum is compilers like MLIR. The approach is to basically have general frameworks and be able to compile to different targets, but they need a lot more work to basically get things right. Especially we have these different interactive components, like you have tiling, you have caching, you have all of these components that interact. So there's a lot of work in figuring out how to order those optimizations to get what you want. So now I'll end the video here, but in this mini series or series, so the follow up, what I'll do is I'm going to go through all of the baselines I've shown you here, the numbers. So I'll go through the code, I'll show the code that I wrote, I'll show the documentation of those libraries. We'll run and I'll show you the numbers, but we'll also go through those frameworks to understand exactly where that vectorization is coming from. Because I've already done this exercise, and all of these libraries are relying on vectorization. So I'll show you how they introduce it either from their code or by looking at the final binary, right? So that's what we'll do. So we'll have multiple videos on this probably. And I have a second part which I want to do, which is basically successfully lower the MLIR code we had earlier to get to vector instruction and close this 1000x gap. But this is a bit of a to do. I have not managed to do this yet. I don't know if I have enough time to pursue this, but that's the high level goal.